What's up, y'all? Today we're going to put on some chemistry aprons and learn about the ingredients and recipes that chemists use to understand the chemical reactions that take place all around us. So get some utensils out, tie your bib nice and tight, and let's chow down. At this point, we know that all matter is made up of tiny particles called atoms. But to understand the changes that occur with matter, chemists need to identify the active ingredient of a substance and determine how much of the substance is actually there. In agriculture, for example, nitrogen is used as a fertilizer, so it is important to know how much of it is in the nitrogen-containing compounds that are used as fertilizers. And we can do this by determining the percent composition of nitrogen in those substances. The percent composition is the percentage by mass of each element in the compound. So we can use the formula of the total mass of the element divided by the total mass of the compound multiplied by 100 to see that this common nitrogen-containing fertilizer, anhydrous ammonia, contains about 82% of nitrogen in it. Another way that chemists like to identify and quantify substances is to determine exactly how many atoms and ions are in that substance. But physically counting the number of atoms in something is basically impossible because they're so small. So instead, an Italian scientist by the name of Avogadro measured masses and volumes of gas particles to determine a mathematical constant for the number of particles in any given substance. The constant he defined, now known as Avogadro's number, is 6.022 times 10 to the 23rd power. And just like we use a dozen to represent 12 or a pair to equal 2, in science, Avogadro's number is equal to 1 mole. By using Avogadro's number as a conversion factor when given the number of moles, we can perform dimensional analysis to determine the number of representative particles in a substance, which could be atoms, molecules, or even ions. For example, if we wanted to determine the number of atoms in 5 moles of carbons, dimensional analysis in Avogadro's number calculates an answer of 3.011 times 10 to the 24th atoms of carbon. Now let's talk about this thing we call moles. And no, we are not referring to that little beady-eyed animal that digs holes. In chemistry, the mole is a unit of measurement used for the amount of substance present. And being that there are different ways to describe the composition of a substance, mole units are used to represent a few different properties of matter. We just seen how we can use moles to count representative particles of a substance, but we can also use moles to determine molar mass, which is the mass of 1 mole of an element or compound, or molar volume, which is the volume occupied by 1 mole of an element or a compound. Each atom or ion has a particular mass, which is defined on the periodic table. And in this example of methanol, with the chemical formula of CH3OH, by adding the atomic masses of all of the elements in the compound, a formula mass of 32.0 AMU can be calculated. And being that the definitions of the mass of an element and a mole were based on the same reference material, carbon-12, 1 mole of a pure element in grams is equivalent to the mass of that element. In other words, 1 mole of a substance is equal to the mass of the substance in grams. With an atomic mass of 12.01 AMU, or 12.01 grams per mole, in 12.01 grams of carbon, there is 1 mole of carbon, or 6.022 times 10 to the 23rd carbon atoms. So the molar mass of a substance is simply the atomic mass of the substance with the units grams per mole. And this also applies for compounds as well. In our methanol example, with the formula mass of 32 AMUs, the molar mass of methanol would be 32 grams per mole. Ultimately, if we are given the mass and chemical composition of any substance, we can evaluate the amount of moles, mass, volume, and representative particles of that substance. By measuring the quantity of matter and establishing a relationship between moles and the number of atoms present in a substance, chemists are able to understand the chemical reactions that take place all around us, all day, every day. All chemical reactions, which are changes in matter that produce something new, are shown by a symbolic representation called chemical equations. And I like to think of these little things as recipes that show us the ingredients and the results of a chemical change. All chemical equations contain the chemical formulas of the starting substances on the left side, called reactants, and the new substances that are a result of the chemical reaction on the right side, called products. The different substances on each side are split up with a plus sign, and the reactants and products are separated by an arrow, which is read aloud as yields. Finally, the number of moles of each molecule or compound is indicated with coefficients in the front of the chemical formula, and the state of matter of each substance is placed after the formulas with an abbreviation in parentheses in subscript form. This equation represents the chemical reaction of methane burning and shows us that when 1 mole of methane combines with 2 moles of oxygen gas, 1 mole of carbon dioxide and 2 moles of water vapor are produced. The number of moles of a substance, the coefficients, are a result of the law of conservation of mass, which just basically states that whatever and however much goes into a reaction must come out in some way, shape, or form. In order to satisfy the law of conservation of mass, chemical equations must be balanced, meaning the number and type of each atom must be the same on both sides. And the only thing that will change will be the arrangement of atoms from one side compared to the other. Now, out of all the chemical reactions that occur in the world, there are 5 major types. Combination reactions, also called synthesis reactions, occur when 2 different reactants combine to form one product, like we see here in this example of hydrogen and oxygen gases combining to form H2O, water. Decomposition reactions are exactly the opposite and occur when one reactant breaks up into 2 products, like when hydrogen peroxide, H2O2, breaks down into water and oxygen gas. Single replacement reactions occur when an element replaces a similar element in a compound, like how we see in this example where the silver element replaces the hydrogen atoms in the compound dihydrogen sulfide, producing silver sulfide and hydrogen gas. In this type of reaction, the element must be similar to the one that it replaces. But for the reaction to even occur, the element must also be more reactive than the one it replaces. And we can determine how reactive an element is by looking at an activity table like this one right here. Double replacement reactions occur when the positive and negative ions of 2 ionic compounds swap partners and produce 2 new compounds, like in this example of sodium bromide and barium chloride swapping partners to produce sodium chloride and barium bromide. The final major type of chemical reactions is the one we discussed earlier when we were talking about the burning of methane, which is just a common way of referring to this type of chemical change, otherwise known as combustion. Combustion reactions occur only in the presence of oxygen, which means it will always be a reactant in a chemical equation representing combustion. And if you think about it, this is the fundamental reason why something is covered when it is burning, to prevent oxygen from reaching the substance and adding to the fire. On the flip side of that, every combustion reaction will always give off heat, meaning it is exothermic, and it will always produce the same products of carbon dioxide and water vapor, otherwise known as steam. Alright y'all, now that you know how to indulge on a mean chemistry cuisine, roll up them sleeves and feed on these appetizers. That does it for today, folks, and you know what that means, but I'm still going to tell you because I'm sick of this nonsense. You matter, darn it, because darn it, you're matter. So what in the world is the matter? Thanks for watching. I'll keep bringing your A game. Have a blessed day.